So in the last class, we were looking at Turing machine. So a Turing machine, basically it also has a state diagram and it has an input tape, unlike PDA or FSM. And this input tape is an infinite tape, closed at the left end and open at the right end. And you have a read-write head, which can go over this input tape, left or right, one step at a time. And it can not only read the symbols, but it can also override some symbols. Okay, so this is Turing machine in short. And another thing is, like another main difference between a Turing machine and a PDA is that in a Turing machine, the input tape and the stack, it's not stack, the memory, both are same. Whereas in a PDA, the input is different. You can imagine that input coming over a tape, but that input tape is like a queue. You cannot go backwards on the tape. You can only go forward one symbol at a time. You cannot go back and forth. You cannot read a symbol multiple times. You can read every symbol only one time. So you can only go forward one symbol at a time in a PDA. The memory is separate. The input tape is separate. Whereas in an FSM, you have only input tape. You don't have a memory. Okay. So in FSM, you have only input tape. You don't have a memory. In a PDA, you have input tape as well as memory. All right. This input tape is like a queue. You can read only one symbol at a time. Whereas in a Turing machine, both the input tape and the memory are combined. So, and on this input tape, you can go back and forth multiple times. You can not only read the symbols, but you can also write symbols, overwrite symbols. So these symbols are not only read from the tape, they are also stored on the tape. Okay, so memory and input are both same in a Turing machine, and you have more freedom in a Turing machine, right? So this same tape can act as a stack, can act as a queue, can act as an array. It can act in different ways. Whereas in a PDA, you only have stack. That's it. Input tape, it's just a linear queue kind of a thing. Okay, in an FSM, you only have a queue kind of a tape. You don't have any memory. All right, so these are some high-level differences between the three machines. Yesterday, we started the example, construct a Turing machine that recognizes the language W#W. I said this language cannot be recognized using a PDA because PDA necessarily uses a stack. If the language were W followed by W reverse, then a PDA can recognize it, but this is not W reverse, W followed by W, which means you should compare the first character of the left half with the first character of the right half, second character of left half with the second character of right half, and so on. Whereas in a PDA, when you are using a stack, you can compare the last character of left half with the first character of right half, and so on. So you go like this. Only that sequence is possible in a PDA. The other sequence, like parallelly going at the same distance, two pointers, it is not possible in a PDA. So this can be necessarily done only using a Turing machine, not a PDA. All right. So the algorithm is simple. Imagine you are given a string, left half, hash, right half. You check one symbol at a time, start with the left half, check the first symbol, cross it, go to the right half, check the first symbol. If it matches with the previous symbol, cross it, come back up to the first cross that you see on your way back, stop there, read the next uncrossed symbol, cross it, go to the right half, read the first uncrossed symbol. If it matches, cross it, come back to the left half, go to the last cross you see or the first cross when you are going back, stop there, again go one step right, read the first uncrossed symbol, cross it, and go on like this in a zigzag fashion. Basically, every symbol you are reading, you cross it and move to the other half. And in the other half, you move only up to the last cross. You need not go through all the cross symbols. Whenever you are, let me say, first cross symbol. Okay. So whenever you hit the cross, stop there, move right. If you are in the left half. If you are in the right half, pass through all the cross symbols until you see the first uncrossed symbol, compare it with the previous symbol. Okay. So why is this? Because all that you have is the tape. You can't say, okay, I won't use I won't cross the symbols. I will just remember the symbols I saw or the position that I saw. Where do you store this position? Like I saw the first symbol, second symbol, third symbol. So when I come back, I will see the fourth symbol. But you need to store these numbers 1, 2, 3 somewhere. Where do you store? There is no other separate memory. All that you have is the tape. So if you have to store that number, again, you have to store it somewhere. Okay. But that number doesn't mean anything to a computer. Even to understand that number, you should do some computation. So without using any numbers, using the tape itself, you should understand where you are. Okay, so we have to use a marker to indicate to us where we are or how much we have seen, not numbers. We can't count, in the sense we don't remember the numbers, we can't understand the numbers. Everything is just a pure symbol to me. And these symbols, all that I can do with these symbols is either match them or don't match them. I don't give any meaning to these symbols. That's all. Okay. So let's work out the example, and then it will be easier. So let's assume I have a string 0111 hash 0111 followed by blank symbols. You see, this is an infinite tape. So the tape won't end with the input. Input will occupy some portion of the tape, the beginning of the tape, and the rest are all blank symbols, infinite blank symbols. And my read write head starts with the leftmost symbol. Okay, so now what I do, I am reading this. I remember this 0, and I will replace this 0 with a different symbol just to indicate to me that I have seen this 0. I have seen this symbol. Okay, so I will cross it. I will replace it with a cross. All right. And then I will move one step right. Now my read write head is on this one. Now I'll continue moving right until I go to the first uncrossed symbol after hash. Okay, so I will continue moving right until I reach the first uncrossed symbol after hash, that is 0. Now this 0 is matching with the previous symbol that I saw. So I have memory in the sense that whatever symbol I saw earlier, that much I can remember, one symbol. So now this symbol is matching with that. I will cross it. I will cross it, and I will keep moving left. I will keep moving left until I reach the first cross that I see while going left. Okay. Now I stop there and I start moving right. I move one step right and I see the next symbol. So I come here. I see this symbol. Now I cross this. I go to the right. I see the first uncrossed symbol. Compare that with this. If it is fine, I will cross it, come back and continue this process like that. Okay. So I'll continue this process until all the symbols are crossed on both sides. So I am left with 4 crosses here, and I am left with 4 crosses here, and I reach this blank. Okay, so which means the left hand side and the right hand side, all of them matched. Now I reach the blank, which means the input is over, everything matched so far. That's it. So now you accept. All right. So let me give you a smaller quick example. So suppose if my string is say 011 hash 011. So first I'm here. Now I cross this, I'm here, right? Now I move here, and then I move here, and so on. I go up to here. I see this is also 0. I cross it. Now I move left. I stop at the first cross. Now I move one symbol right. I see a 1. I remember it and I cross it. I keep moving right until the first uncrossed symbol. I am here. I see a 1 here also. So I cross this one and I keep moving left until I see the first cross. I need not look at these crosses. I just stop at the first cross. Now I stop here. I go again one step right. I cross this. I remember it's a 1. I keep going until the first uncrossed symbol here. I see this is also a 1. I cross it. I keep going left to the first cross. I stop here. The next one is a hash. So left half is done. Now, while going to the right half, I should see a blank. If I don't see a blank, something is mismatching. If I see a blank, yes, accept. That's it. Okay. All right. Now let's move on to the next section, that is configuration of a Turing machine. A configuration of a Turing machine is composed of three things. So what are those three things? Current state, current tape contents, and current head location. So let's try to understand it visually. So imagine you have a Turing machine in some state, say Q3. And you have an input tape with the symbols say 1, 0, 1, 1, 0, 1, followed by blank symbols. And let's imagine the read-write head is on this one, the fourth symbol. Okay, so this is the current state, that is Q3. These are the current tape contents, 101, 101, followed by blank symbols. And this is the current head location. Okay, now this input can be divided into two parts. The input before the head and the input after the head, including the current symbol, goes in the second half. So before the head, we call it S, and after the head, including the current symbol, we call it T. Sometimes we may need to deal with the current symbols, the current symbol and its neighboring symbols. In that case, we separately mention those symbols and group the remaining parts under variables. So sometimes, like, we group this into U and this into V. Head is on 1. Okay, and we call this V. You'll understand it just in a minute. And this 1, 1 we write separately. So the configuration can be represented as So there are multiple ways in which we can represent this configuration: 101, Q3, 101. So now this is a diagram. We have an arrow, we have some state, we have some input. But if I have to linearize it, if I have to write it in one line, then I have to give all this information in some way, right? So I have to mention the state name. I have to insert it at some position in the string. So where do I insert? Just before the symbol which it is pointing to. Q3 is pointing to the fourth symbol. So I insert it just before that. So when you write the state name in a string, it means the state is pointing to the immediate next symbol. That's what it means. The immediate right symbol. Okay. So you need to understand that. And so either it can be written like this, or it can be written as S Q3 T, which means Q3 is pointing to the first symbol of T, string T. S and T are strings. Or it can also be written as U1 Q3 1 V. Right? Here only 1 0 are in U, and then 1 is there separately. And then Q3 you write, and then the one which it is pointing to you write, and then the remaining symbols as V. You will see why we need this separation just in a minute. Okay. So say delta 1 Q3 comma 1 is equal to, so what we do, the one which Q3 is pointing to, we replace it with a 0 and we move one step left and we update Q3 to Q4. We change the state. Okay. So this configuration can be seen as either like this 101 Q3 101, or it can be visualized as, suppose I have my string 101 101 and Q3 is pointing to this. Okay. Now I am modifying this as Q40L, which means, so my second configuration will be, so it will be easier here to understand. So my read write head is on this one. I will overwrite this one with a 0 and I will move one step left and I will update my state from Q3 to Q4. Okay. So this will become 101. This one will become 0 0 0 1. Earlier Q3 was pointing at this location. Now it moves left. So it becomes Q4 and it points to this one. Basically, you are on the tape, you are pointing to a symbol, you are overwriting it with a different symbol and moving either left or right. In this case, we are overwriting 1 with 0 and moving left. Okay. This is just an example to understand configuration, concept of configuration. This thing, how do I write it here? This thing, 1 0 Q4 1 0 0 1, which means Q4 is pointing to this one. Okay. So if I want to say, I can say this is my U, this is my V. This UV will remain the same. This is my U, this is my V. Okay. So then U1 Q3 1V changes to, how do you express it in terms of UV? U Q4 1 0 V. Okay. So this is the result of my delta 1, and same thing expressed in a different way. Okay. Left, move left. You replace the symbol and move left. If it is R, move right. So I'll give another example with R. Say delta 2 Q3 1 equal to Q4 1 R. So what is this saying? Right now Q3 is pointing to 1. You keep that 1 as it is and you move right by 1 position and you update Q3 to Q4. Okay, so here say the first configuration is the same 101 Q3 101. If you have to depict it visually, it is 101 101 and Q3 is pointing to this one, right? This is my U, this is my V. Now when I update the configuration, so first let's do it here, it is easy. So I have 101 101. Now Q3 keeps this one as it is, moves right by 1 position and it becomes Q4. So it will be Q4 and pointing to this 0. Okay, and still this is my U, this is my V. Now how do I write it as in terms of ones and zeros? 1 0 1 1 Q4 0 1. Okay, in terms of UV, how do we write? Initially it is U1 Q3 1V changes to U 11 Q4 V. So it means Q4 will be pointing to the first symbol of V. Okay, so basically if you use S and T, you won't leave any symbols in between. Entire left half or left portion is in S, entire right portion is in T. If you are using UV, the middle symbols you are specifying explicitly. Okay, that's all. So we say that, okay, so here this is the output of delta 2. Okay, we say that UA QI PV yields U QJ A CV if delta QI B equal to, so can you guess what are the 3 things here? So what is happening here? Initially QI is pointing to B, then what is happening? B is replaced with A. B is replaced with C, and you are moving left or right? Left. That's it. So B is being replaced with C and you are moving left and QI is updated to QJ. This is QJ, new state. Okay. So U and V, they are strings. U is a string, V is a string. Whereas A and B, each one of them is one symbol. They are not strings. Okay, A is one symbol, B is one symbol. All right, and here yields is the keyword. Yields is like derives. In grammar, one string derives another string. Similarly, one configuration yields another configuration. Okay, and in this, first this replacement happens. B is replaced with C, then it moves left, then QI is updated to QJ. Okay, so let's break it down further. So suppose I start with UA QI BV. It is finally updated to U QJ A CV. Okay, but you can still break it into sub steps. First, what happens? B is replaced with C. So it becomes UA QI CV. Then this pointer moves one step left. So it becomes U QI A CV. Then this QI becomes QJ. Okay. So this is the first step where B is replaced with C. In the second step, QI moves one step left. In the third step, QI becomes QJ. So that is what these 1, 2, 3 are indicating. In the first step, B is replaced with C. Second step, it moves one step left. Third step, QI becomes QJ. Okay. Or in other ways, you can write it as, you can depict it slightly differently. My string is UABV and QI is pointing to this B. Finally, it becomes UACV and QJ is pointing to this A, right? So again, show the sub steps. First, this B is replaced with C. So it becomes UACV and QI remains the same. And then in the next step, QI moves left by one position. QI points to A. In the final step, QI becomes QJ. Okay. Fine. Yeah. So let me color them differently to understand the difference in arrows. Okay. Now let's move on. We say that UA QI BV yields UA C QJV if delta QIB equal to, so what should I write here? QJ C R. Here QI was pointing to B, then it moved right. It changed it to C and moved one step right. Okay. C1 yields C2 if the Turing machine can go from C1 to C2 in a single step. Okay. But there is a special case. Can anyone guess what the special case is? In a Turing machine, there is a special configuration. And you need to handle that separately. Special transition. Huh? Not the blank space. The other end. What if it is pointing to the left end of the tape? And when it is pointing to the left end of the tape, what if you are given an instruction to go left again? It can't go further left, right? So it will remain there. But if it has to replace something, it will replace something and remain there. Okay. So for the left hand end the configuration QI BV yields QJ CV if the transition is left moving and it yields CQJV for the right moving transition. Okay, clear? All right, now let's look at the formal definition of a Turing machine. A Turing machine is a that is Q, sigma, gamma, delta, Q naught, Q accept, and Q reject. So this Q reject is the additional thing here. That's why it's a 7 tuple. PDA was 6 tuple, where Q, sigma, gamma are all finite sets and Q is the set of states sigma is the input alphabet, not containing the blank symbol. So blank symbol is not part of the input. If blank symbol is also part of the input, then the input is always infinite, right? Because you have infinite blanks. So blank is not part of the input. The moment blank starts, your input ends. Blank is part of the tape alphabet, not the input alphabet. Okay. So even if you have some character like space, that space will be different from blank. Okay. So blank is basically a symbol which is never part of an input alphabet. You cannot use it in any input. Okay. Not containing the blank symbol. Third, gamma is the tape alphabet where blank belongs to gamma and sigma is a subset of gamma. Okay, this is clear, right? Because we don't have a distinction between the tape, input tape and the memory tape. Both are same. So all the input symbols also go on to the tape and all the sort of memory symbols also go on to the tape. So blank symbols are on the tape, and say when you cross a symbol, that cross mark is also belonging to the tape alphabet, not the input alphabet. Okay, so these are tape symbols. Fine. And fourth, delta. So can anyone tell me what is the domain and range of delta? Q cross sigma. Q cross gamma. That is the domain, and the range is Q cross gamma cross the set L and R. Okay, so this is the transition function. So for instance, if I take this example like delta Q31 equal to say Q4 0 L. So what is this saying? This is coming from Q. This is coming from gamma. Why gamma? Because we may have transitions including blank also. And in the previous example where we crossed a symbol with cross marks, that will also play a role later. So that cross mark is not part of the input alphabet, it is part of the tape alphabet. So tape, the largest set you should take, tape alphabet. Okay, so this you will cross, and this comes from Q, this comes from gamma, this comes from L and R set. So cross. Okay. No. Epsilon, there is you can have epsilon, but it will be handled with. So let's see an example. You will understand. Okay. Q naught belongs to Q is the start state. Q accept. Technically, you will have, because if you have it in PDA and NFA, you will have in Turing machine also. So yes, you will have epsilon transitions when necessary. This is the reject state. And where Q reject is not the same as Q accept. Both states should be there, both are different, both cannot be the same. Okay, so this is the formal definition of a Turing machine. Now what will we get next once we look at the formal definition of a, yeah, now formal definition of computation for a Turing machine. Okay, the start configuration of Turing machine M on input W is Q naught W, right? It is pointing to the first symbol of W, and the start state is Q naught, so the configuration is Q naught W. Okay, a Turing machine accepts input W if a sequence of configurations C1, C2, and so on up to CK exists where C1 is the start configuration of M. On input W. Each CI yields CI plus 1 and CK is an accepting configuration. In an accepting configuration, the state of the configuration is, what will be the state of the configuration in an accepting configuration? You accept. In a rejecting configuration, the state of the configuration is Q reject. Okay. Now let's look at the language recognized by a Turing machine. A language is called Turing recognizable if some Turing machine recognizes it. It is also called a recursively enumerable language. A Turing machine generally 2 minutes. A Turing machine generally, you have a class after this? Huh? No, right? Yeah. A Turing machine generally may either halt, yeah, 2 minutes. It may either halt or loop. Here looping is generally understood as infinite looping. But there are some Turing machines which always halt. That is either accept or reject. So like I said earlier, halting does not necessarily mean only accepting. Rejecting is also halting. Only if it is neither accepting nor rejecting but going in an infinite loop, then it is not halting. Okay? Such Turing machines are called deciders. Okay. A language is called Turing decidable or simply decidable if some TM, some Turing machine decides it. Decides means recognizing. It is also called a recursive language. So basically, recursive languages are a proper subset of recursively enumerable languages. Or, in other words, Turing decidable languages are a proper subset of Turing recognizable languages. So we won't have time to go into more depth regarding this. The only point which you need to understand is Turing recognizable languages are also called recursively enumerable languages. That's all. If you take just this point, that is enough. There are other sections where this is explained, other chapters, but we won't have time to go into that. Just take this one point. Turing, if you remember that chart, hierarchy of languages, Chomsky hierarchy, you remember those languages which are recognized by a Turing machine, those are called recursively enumerable languages. That's all. Okay. So let's stop here today. In the next class, we will look at a couple of examples of Turing machine with state diagrams, and we'll close. Okay.